Well, thank you for joining us today. And today we're going to demonstrate the IPC Compliant Wizard and Altium Designer. You can see that I have my screen up over here. I am currently in the PCB library editor, so that's where you will find this particular tool. You will not find it in the PCB editor. So make sure if you're opening up Altium Designer for the first time, you go into File, New, go into your library, and under here you'll find PCB library, and you will see the same screen that I'm basically seeing here right now. If the library does not open up over here, and Altium does not always open up the PCB library tab, make sure that you go over to PCB down here at the bottom right here in corner and make sure that this is enabled, and then you should be able to see this particular tab listed on the screen. Okay. So what I'm going to do now is I'm going to show you where it's at. It's under Tools, and then you have IPC Compliant Footprint Wizard, and you'll click on that. Now at this point in time, I'm going to cancel this for a moment, and I'm going to move a few things over so that I can show you the wizard, and I can also show you the data sheet at the same time. So I'm going to cancel here, and I'm going to move this over to my other screen, and I'm going to bring up the SOIC component that we are going to create for this particular demonstration. So I'm now going to, on my other screen here, I'm going to go under Project, or pardon me, Tools, IPC Footprint Wizard, and I'm going to bring that over here to the other screen so we can see both of them. At this point in time, we really don't need the rest of Altium Designer, and the wizard's going to lock it down anyway, so we can't make any additional edits or adjustments to the other screen until we are done with the wizard or until we cancel it. Okay, so here's our component and here's our wizard. We're going to begin it here. So the next step is to tell it what type of package there is out there, and we are using an SOIC. Okay, and we'll press next. And by the way, I'll make a mention. I will make mention of the fact that pretty much I'm going to say 98% of all the companies out there that make these components try to adhere to the IPC standards when it comes to packaging. A lot of them aren't going to create their own types of packages. They really want to work with the standards out there. And that works, of course, to our advantage, especially when we're creating libraries. It allows us to use these type of wizards. The only time where I've ever seen any odd or unusual types of shapes are those parts, especially like memories, where they're trying to stack things or they're trying to do things to try to make them more efficient. But generally speaking, almost everybody tries to comply with these packages simply because they want to hand off their chips over to a packager and to make these things in massive volumes, and that they work, again, with everybody's libraries. So I'm going to press Next over here, and you can see that they give you some default dimensions here. And one thing you should notice is that the way that they set these up over here, meaning Altium, may not necessarily match up with the way they have them over here on the sheet. So you have to be a little bit careful about how you work these. Okay. So the first thing we're going to do is we're going to enter all of these in here, and we're going to make sure that we do these correctly. Now you can see that these are all done in millimeters. If we go over here, you'll notice that these are done in millimeters as well. Now depending on the spec sheet, some of them are going to be done in millimeters, and some of them are going to be done with both millimeters and in mils. Okay, though a lot of companies are slowly but steadily pushing towards millimeters since that is becoming the standard internationally. So let's take a look here. We've got the wide range H. So the first thing we need to do is understand what width range H. So this is what we're looking at over here. So by this definition, it's looking for the length of the component from a side view, from basically the tip of one gull wing all the way to the tip of the other gull wing. So if we go over here and look on our spreadsheet over here, interestingly enough, they're not really. They're showing it over here, and they're calling it E. So here you can see how they're calling it H over here, and over here it looks like H, but actually they're showing it as a part of E. So when we take a look at E and we follow it down over here, they're calling it 6 BCS. Okay, if you actually look at it, it says 6.00 BSC, so I need to correct myself from earlier. Well, what does BSC what does it mean? And if we go over here to the notes, and I'll drop this down a little bit over here, you'll see that it's a basic dimension. They're not giving any tolerances for this. So if we're going to put this in over here for the width range, what we're going to put in, and I don't think we need to put the millimeters since these are all being done in millimeters, we just put in 6.00 for both of these. Okay. Now normally you'd want to have this tolerance in there, they're not providing it, then so be it. But these can definitely range a couple of mils, or in this case, even you could see a millimeter that it was where there was a change. But let's go over here to the maximum height. And by the way, as I'm moving about doing this, you'll notice that the preview over here has changed. So Altium is going to try to create the 3D for this as we're moving about through these numbers. So the maximum height over here does match up with what they put over here. So the A here does match up with the A over here, and they're giving a maximum height of 1.75. So we'll put that in. Okay. The standoff height, which is A1 here, they're basically saying how high that the particular gull wing lead is, and that does have a range. In this case, they're showing from 0.10 to 0.25. Normally what you want to do is you want to take worst case scenario, especially when you're dealing with the leads and the board here. So we're going to give this over here 0.25. And that's for the minimum standoff. Okay. For the body width range, this is E. So now we're just talking about the body itself, not the entire range. And they give that over here as E1. All right. And again, they're giving us just a very basic number. They're not giving us any tolerances, so we'll put the same number in for both of those. And 3.9. Okay. The body length, which is D, so it's basically how long this is, matches up with what they're providing here. And again, they're going to give us just a basic number, and that is 4.9. All right, so for the number of pins, we are going to put in 8 of them, because you can see over here that there's 4 on each side, and you will see this automatically adjust in the 3D view once we put that in there. Okay. The lead width range, which is B, okay, and they show this over here, is basically how wide the pad is. Okay, and if we go over here to B, you can see it's 0.31 as a minimum and 0.51 as a maximum, and those match up exactly, which is great, so we don't have to make any changes here. For the lead length over here, and that again is L, so what they're looking for is how much lead is actually sitting on the pad, and you'll see that over here on the spec sheet is between 0.4 and 1.7 millimeters, and they've got the exact same thing over here, which is good, because what that is saying is that what Altium put in here as a part of the IPC specification is matching up with the package specifications for this particular component. And do remember one thing, that some of these things can fluctuate around, but the fact of the matter remains is that all SOIC packages have a pitch of 1.7 millimeters, and that's something that just simply cannot be changed, or otherwise you change the definition of what an SOIC is, and it's probably a different component. There is one modification I do need to bring to your attention. The minimum standoff height here is 0.25, and you can look over here and it shows that it is between 0.10 and 0.25. Now I did make a mistake earlier saying there was 0.25, and normally when we are creating these footprint pads, you want to go for the maximum, what they call the maximum material condition, to make sure that if they are using more materials than usual, or because of the way the processes are set up that particular day, that these components will fit on their pads. However, in this case over here, they are specifically looking for a minimum standoff height, and in this case we will oblige by giving it, changing this from basically 0.25 to 0.10. So at this point everything has now been matched up, and the 3D visual is giving us a good indication that things are looking pretty good. So now we're going to press next and take a look at the next page of the wizard. Alright, on this page over here they're basically asking for what's called a thermal pad, and on a lot of components, especially those that run extremely hot, you can add a thermal pad underneath it in order to help dissipate the heat from the component. In this particular instance, it's a small component and it doesn't draw that much wattage, so there's no need, and there's nothing in the specification requesting for such a pad to exist. Most companies will throw down a statement saying, hey, please put this thermal pad down, but in this case over here we can ignore that since there is no need for one. Now, one other thing I'm going to mention as we're going along is if you want to see some more information here, you do have the ability to modify this and move it around. So for example, if you want to see how the underside of this looks, well, you basically use the same command set that you'd normally use if you're in 3D. So on my keyboard, I'm going to hold down my Shift key. I am going to right mouse click, and that's normally what you do in order to rotate it. And if I start moving my mouse around, I can start looking at the bottom side to see how things are coming together. Okay. If I want to see the 2D, then I go over here where they have this little hammer and filter, and I can click on that and I can say turn off the 3D, and it now actually shows me the 2D version of this. Okay. So I'm going to go back to the 3D and then we'll move on to the next page here. This page over here talks about the heel spacing, and the heels are very important, especially when you're doing the soldering, because it's ultimately the heel that really needs to make contact of the 4 points you have. It's the one that needs to make the most contact with the solder and the pad itself. However, in this case over here, especially since they didn't give us any specific values for this, we will use the calculated values. We'll move over to the next page. Okay, over here they're going to talk further about the SOIC solder fillets. Now, if you're not familiar with them, let me give you kind of a brief overview. There's 4 sides that you have to worry about when you're doing soldering. You have the toe, which is basically the end of the gull wing, which is right over here. You have what's the heel, which I had mentioned earlier is one of the most important areas that needs to be soldered, which is where the joint or the L begins from basically the pad up to the component itself. And then you have the sides, and there's, of course, of them. There's 2 of them. There's one here and there's one over here. And what this allows you to do is to adjust the pad based on what you think you need for additional clearances to make sure that this will fit on there and that you'll have enough solder. So for the toe, it basically lengthens it one way. The heel lengthens it the other way towards the component, and the side is going to make it a little wider. Now, of course, you got to keep in mind that the wider you make this, the less pitch you have between the others. Normally, again, because you're using an SOIC and there's a very specific pitch, you wouldn't really adjust this all too much because you want to keep to the pitch that's already been recommended. You can turn this off and they'll give you access to all 3 of these, or you can also do what's called a board density level, and this is just based upon how many components or how dense these boards are going to be, and that's kind of hard to judge based off of but the fact that you're simply putting together a library, you don't even know where the application is going to be for this. We just recommend that you leave this as is, and you can always make these adjustments certainly thereafter in the library if you think you need them, or even in the PCB itself if you're really getting into a situation there. But we're going to move on to the next one. Now on this page over here, they're talking about component tolerances, and you probably noticed at the very beginning what Altium had put in were the recommended ones by the IPC, and a lot of times the packages are going to have a little bit of a deviation from that because of whatever packaging situation that whoever they're using to create that package, or if there's some other situation where they had to make it a little bit wider and so on and so forth. So this is an opportunity over here that based on the supplier you can try to add a little bit of tolerance in there. But for this case over here, we're going to use what they call the calculated component tolerances that we put in on the first page. All right, and this is a continuation of the SOIC IPC tolerance page. This is kind of an interesting page because what they're trying to allow you to do is to account for both fabrication and assembly issues. And again, I think this is kind of a hard thing to do, especially in the library, given the fact that most people don't know which fabricator or assembler that they're going to use. So you can adjust these values, but we're going to leave them as the default values as they stand. Alright, this is for the footprint dimensions, and it gives you the opportunity to make a few more adjustments to the footprint if you see fit. So for example, over here the pad dimensions over here are allowed if you turn this off, and you can change the X and Y. You're also given the opportunity to change the pad spacing over here as well. One of the things that we're going to do is I'm going to change this over here to the 2D mode, because one thing we are going to change over here is we're going to go from the rounded to the rectangular. Okay. And it's always a personal preference, though in this case I prefer the rectangular here. The next page that we're on over here is the SOIC silkscreen dimensions, and one of the things that's really important is to note the silkscreen line width here, which is at 0.2 millimeters. The industry standard is 5 mils, and that equates to 0.127 millimeters. So Altium is giving you quite a bit of space over here for this, and that's good. We don't recommend that this be changed, again, because of fabrication issues that you may come across if you try to make it too small. The other thing here too is you'll notice that they have the silk underneath the component. If you wish to make the silk larger, this is your opportunity to do so, both in the vertical and the horizontal direction. Let's click over here to next. Alright, now this one over here deals with what they call the courtyard, the assembly, and the component body information. So the courtyard is best described as a bounded rectangle, and you can see a demonstration of it over here. It's a line that you put in. It's not the silkscreen, but it's put on a mechanical layer in Altium Designer, and it basically is giving you a reference from a 2D point of view as to where the component is going to spread out to. Now in this case it's pretty straightforward, but if you had something that had a little more size, or maybe like a connector where something was overhanging on it, you'd want to make sure that in the end that you made a courtyard to accommodate that mechanical aspect of it. There's also the assembly information as well, and the assembly information is usually kind of kept separate from the courtyard, where the courtyard is really more of a 2D view of where things are being laid out. The assembly information is more specific to what you're going to give them for their pick and place and how things are going to lay out. So the courtyard could be the exact same thing, but sometimes you may draw it a little bit smaller. Now, one thing that's really important to mention over here is that you got to be consistent with your mechanical layers. And there should be a consensus amongst your group, especially if you're working with other people, as to what those mechanical layers are going to be. Because if you're doing it one way and another person's doing it another way, in the end you're going to have a scramble, and you're going to be doing a lot of modifications to the printed circuit board so that you have one sheet that is dedicated to your courtyards and another sheet that's dedicated to your assembly. So it's really important that you agree to how you want to do this. Now Altium does have some guidelines on this, and if you contact them or send them an email through their case system, they'll provide it to you. It could also possibly be on their forums as well. I haven't checked, but it's something to take a look at or to ask people for as to how they set those up. But in the end, it's ultimately up to you to do that. There's no set IPC standard for those layers. You've got to come up with the ones that everybody's going to agree to. Now in our particular instance over here, we use mechanical layer 6, and that's where we're going to change this. One other side note, though, I think this is becoming less and less of an issue. In the prior versions of Altium Designer, I believe in the Altium 6X series, prior to when they started doing the summer and the winters and Altium 10, there was only 16 layers, and they changed it out to 32 layers. If you are working with someone who's using a very old version of Altium Designer, you want to be aware of the fact that any layers, in particular layers 17 through 32, if you're using an older version of it, they're just going to dump it on layer 16. So you may want to try to stay to the first 16 layers if you're working with anybody who's using an older version of the tool. Otherwise you're going to have some problems with it. But I think that as time has gone on and most people have upgraded to the latest tools, that's probably becoming less and less of an issue. The last section over here is the component body information. This is basically the 3D model of it and where it's going to be placed, because those 3D bodies are put on mechanical layers. But right now we're going to leave everything as calculated, and we'll move on to the next step. This is simply giving a name to the component, and if we take a look over here, what the default is the SOIC, which is the package type. It's showing the 101 or 1.27 millimeter pitch. 600 is the height, and 600 is the length, and 175 is the height, with 8 pins. So if you want to change this, you can turn this off, and then it makes it changeable over here. Some people like to change this, or they have their own formats for it, and that's perfectly fine as well. And then the description as well, you can make a change. So once this component is completed, this is exactly how you're going to see it listed, and we're just going to leave it as is. Alright, and on this over here for the footprint destination, Altium gives you several options. One of them is to simply use the library that you have open. Another option is to create a brand new PCB library file. And the third option is to just open up one library that does exist but you don't have open. So they give you a couple of options here. And then once we press next, or we could have pressed finish, we are complete. And once we press finish over here, I will bring back the screen. Okay. And I will do a VF so that we can see it over here. And here is the completed item. So this is the completion of our component. If I double click over here, you'll see the name as we had indicated earlier. By the way, the N means nominal. There is a minimal and there's a maximum as well. I think the minimal they show is M and the other one is L. It could be vice versa. But we are doing the nominal for this. And then you can also see the description as well. And of course you can change these if you so see fit. There is also a height over here. It's a default height. It's actually kind of legacy from the old 3D. But it's information that it can use. In the event you do not provide a 3D model for this, Altium can use this in its steadfast. It's better to use the model, especially if you have situations where it's an unusual shape, because Altium can do a better job of calculating and showing those clearances, or if there's something that's going to abut against each other. But this is a bit legacy, but it can use it as a part of its design rule set. In addition to that, if I hit the 3 key over here, you can see, once I zoom in over here, that we do have the 3D based off of the dimensions that we provided. You will notice that it did not give us any gull wings over here. It just strictly gives us the body. And for the purposes of mechanical fit, that is more than adequate. So thank you for joining us, and we hope to present on other topics similar to this in the very near future.